All right, in this video, we're going to define the covariant derivative. But before I do so, I want to look at an example and sort of argue that the definition that I'm going to give at the end makes sense. So we're going to start by letting S be some regular surface, and then we take some vector field on S. And we also take a separate vector in one tangent plane of S. And now the question that we want to answer is, how do we make sense of the directional derivative at this point P of the vector field W in the direction of V? Now, let's look at this very specific example. So here we have the cylinder, and we imagine that we have this specific vector field which just sort of runs around the cylinder. Now, we might argue that if we are standing on the cylinder somewhere and we start following this vector field, then really it doesn't change at all. So from our outside perspective, we can see that this vector sort of twists in 3D space. But if we imagine ourselves as living on the surface of the cylinder, we can't see that twisting. So let me just draw a curve on this surface, which I'll call gamma. So from our outside perspective, we see that this vector field rotates as we follow the curve gamma. So if we imagine we're living on the surface of the cylinder, then the direction that this vector field changes in is something that we can't observe. So let's keep working on this example. So we're looking at the cylinder. And for concreteness, that consists of the triples x, y, z, and R3, where x squared plus y squared is equal to 1, and z is free. And now this vector field is given by the function w of x, y, z. So this function has domain the cylinder, and it will send this to minus y, comma x, comma 0. Now I'll use this as an example, but it's a good exercise to check that I can actually do that, by which I mean that check that W is actually a vector field on C. So that boils down to checking that W of P is in the tangent plane to S at P for all P and S, and that it's smooth. Now in the picture we had this curve gamma. So as an example, let's take the curve cosine t, sine t, and 0. This is certainly a curve in S. And now we can take the directional derivative of W for the moment acting as if it's a function not on the cylinder, but just on R3. And we're going to take t equals 0, so we're going to look at the directional derivative at the point 0, 1, 0, 0. and we're going to take it in the direction of gamma prime of 0. Which is 0, 1, 0. And that is given by definition by the following expression. So we compose W with gamma, then differentiate at t equals 0. So we start by just substituting gamma and W. And then the result is the vector minus 1, 0, 0. So let's draw in a picture what we just did. So from a top-down perspective, the cylinder just looks like a circle. And we were interested in the point P, which was 1, 0, 0. Then we had the curve gamma, which just runs around the circle. And we had the vector V is equal to 0, 1, 0. And then we calculated this derivative, which was minus 1, 0, 0. So we see that indeed, that does not lie in the tangent plane. So if you live on the cylinder, this is something that you can't observe. So now if we project this result onto the tangent plane at that point, we get the 0 vector. So we took the directional derivative of this function, but we viewed it as a function into R3 instead of just into S. And then we got this tangent vector, or the directional derivative was this vector. And now I'm saying, well, we should project that to the tangent plane to get information about what that we could see if we lived on the surface. And then we get the 0 vector, which is what we expected. Now I'll conclude with the general definition of the covariant derivative. So let's state what data I need. So S in R3 is a regular surface. W is a vector field. P is a point in S. And V is a tangent vector to S at that point. And then I define the covariant derivative as follows. So it's going to be the covariant derivative at the point P of the vector field W in the direction of the vector V. And it's given by, well, we need to end by projecting onto the tangent plane. So this P stands for the projection onto the tangent plane. And what do? Well, we take the directional derivative of W composed with gamma. And we'll denote this covariant derivative by capital D in the direction of V of W evaluated at the point P. So for this to make sense, V needs to be a tangent vector to S at the point P. And for completeness, gamma needs to be a curve into S, which at 0 gives the point P, and whose derivative at 0 is the vector V. And of course, we should show that the result does not depend on the choice of gamma, only on P and V. So that's perhaps a good exercise. And also just let me write down this PTPS is the map from R3 to TPS, which is the orthogonal projection. So this is the definition of the covariant derivative, and it generalizes the idea of the directional derivative to make sure that we get something which is intrinsic to our manifold S.